Hello, my amazing tribe. I'm excited to connect with you through this video. Thank you for choosing our video on Surya Siddhanta. Sit back, relax, and enjoy the ride. The Surya Siddhanta is a Sanskrit treatise in Indian astronomy dated to 4th to 5th century, in 14 chapters. The Surya Siddhanta describes rules to calculate the motions of various planets and the moon relative to various constellations, diameters of various planets, and calculates the orbits of various astronomical bodies. The text is known from a palm leaf manuscript and several newer manuscripts. It was composed or revised probably c. 800 CE from an earlier text also called the Surya Siddhanta. The Surya Siddhanta text is composed of verses made up of 2 lines, each broken into 2 halves, or pãds, of 8 syllables each. As per al-Biruni, the 11th Persian scholar and polymath, a text named the Surya Siddhanta was written by Lāṭadeva, a student of Aryabhatta I. The second verse of the first chapter of the Surya Siddhanta attributes the words to an emissary of the solar deity of Hindu mythology, Surya, as recounted to an asura called Maya at the end of Satya Yuga, the first golden age from Hindu texts, around 2 million years ago. The text asserts, according to Markandeya and Srivastava, that the earth is of a spherical shape. It treats Earth as stationary globe around which Sun orbits, and makes no mention of Uranus, Neptune and Pluto. It calculates the Earth's diameter to be 8,000 miles modern, 7,928 miles, the diameter of the Moon as 2,400 miles actual, and the distance between the Moon and the Earth to be 258,000 miles now known to vary, 221,500 252,700 miles. The text is known for some of the earliest known discussions of fractions and trigonometric functions. The Surya Siddhanta is one of several astronomy-related Hindu texts. It represents a functional system that made reasonably accurate predictions. The text was influential on the solar year computations of the lunisolar Hindu calendar. The text was translated into Arabic and was influential in medieval Islamic geography. The Surya Siddhanta has the largest number of commentators among all the astronomical texts written in India. It includes information about the mean orbital parameters of the planets, such as the number of mean revolutions per Mahayuga, the longitudinal changes of the orbits, and also includes supporting evidence and calculation methods. In this section, we'll be shedding light on textual history and its impact on our understanding of the subject. In a work called the Pāka Siddhantika composed in the 6th century by Vahamihira, 5 astronomical treatises are named and summarized: Pāla Siddhanta, Romaka Siddhanta, Vaisesha Siddhanta, Surya Siddhanta, and Pāmaha Siddhanta. Most scholars place the surviving version of the text variously from the 4th to 5th CE, although it is dated to about the 6th BC by Markandeya and Srivastava. According to John Bowman, the version of the text existed between 350 and 400 CE wherein it referenced fractions and trigonometric functions, but the text was a living document and revised through about the 10th. One of the evidence for the Surya Siddhanta being a living text is the work of medieval Indian scholar Aryabhatta, who cites and then quotes 10 verses from a version of Surya Siddhanta. But these 10 verses are not found in any surviving manuscripts of the text. According to Kimplovka, large portions of the more ancient Surya Siddhanta was incorporated into the Pāka Siddhantika text, and a new version of the Surya Siddhanta was likely revised and probably composed around 800 CE. Some scholars refer to Pāka Siddhantika as the Old Surya Siddhanta and date it to 505 CE. Based on a study of the longitude variation data from the text, Indian scientist Anil Nayan in 2010 concludes that the text has been updated several times in the past, with the last update around 580 CE. Nayan obtained a match for the nakshatra latitudinal data in the period 7,307,800 BCE based on a computer simulation. In the next segment, we'll be exploring Vedic influence and its implications for our subject matter. The Surya Siddhanta is a text on astronomy and timekeeping, an idea that appears much earlier as the field of Jyotisha Vedanga of the Vedic period. The field of Jyotisha deals with ascertaining time, particularly forecasting auspicious dates and times for Vedic rituals. Vedic sacrifices state that the ancient Vedic texts describe 4 measures of time: Savana, solar, lunar, and sidereal, as well as 27 constellations using Taras stars. According to mathematician and classicist David Pingree, in the Hindu text Aryabhatta BCE or older, the idea already appears of 28 constellations and movement of astronomical bodies. According to Pingree, the influence may have flowed the other way initially, then flowed into India after the arrival of Darius and the Achaemenid conquest of the Indus Valley about 500 BCE. The mathematics and devices for timekeeping mentioned in these ancient Sanskrit texts, proposes Pingree, such as the water clock, may also have thereafter arrived in India from Mesopotamia. However, Yukio Hashi considers this proposal as incorrect, suggesting instead that the Vedic timekeeping efforts for forecasting appropriate time for rituals must have begun much earlier and the influence may have flowed from India to Mesopotamia. Hashi states that it is incorrect to assume that the number of civil days in a year equal 365 in both Indian Hindu and Egyptian Persian year. Further, adds Hashi, the Mesopotamian formula is different than Indian formula for calculating time. Each can only work for their respective latitude, and either would make major errors in predicting time and calendar in the other region. Kim Plofker states that while a flow of timekeeping ideas from either side is plausible, each may have instead developed independently, because the loan words typically seen when ideas migrate are missing on both sides as far as words for various time intervals and techniques. As we move forward, let's uncover the untold stories and fascinating intricacies of Greek influence. It is hypothesized that contacts between the ancient Indian scholarly tradition and Hellenistic Greece via the Indo-Greek kingdom after the Indian campaign of Alexander the Great, specifically regarding the work of Hipparchus II BCE, explain some similarities between Surya Siddhanta and Greek astronomy in the Hellenistic period. For example, Surya Siddhanta provides table of signs function which parallel the Hipparchian table of chords, though the Indian calculations are more accurate and detailed. According to Alan Cromer, the Greek influence most likely arrived in India by about 100 BCE. The Indians adopted the Hipparchus system, according to Cromer, and it remained that simpler system rather than those made by Ptolemy in the 2nd century. The influence of Greek ideas on early medieval-era Indian astronomical theories, particularly zodiac symbols astrology, is broadly accepted by the Western scholars. According to Pingree, the 2nd CE cave inscriptions of Nasik mention sun, moon and 5 planets in the same order as found in Babylon, but there is no hint, however, that the Indian had learned a method of computing planetary positions in this period. In the 2nd CE, a scholar named Yovansvar translated a Greek astrological text, and another unknown individual translated a second Greek text into Sanskrit. Thereafter started the diffusion of Greek and Babylonian ideas on astronomy and astrology into India. The other evidence of European influential on the Indian thought is Romika Siddhanta, a title of one of the Siddhanta texts contemporary to Surya Siddhanta, a name that betrays its origin and probably was derived from a translation of a European text by Indian scholars in Ujjain, then the capital of an influential central Indian large kingdom. According to mathematician and historian of measurement John Roche, the astronomical and mathematical methods developed by Greeks related arcs to chords of spherical trigonometry. The Indian mathematical astronomers, in their texts such as the Surya Siddhanta, developed other linear measures of angles, made their calculations differently, introduced the versine, which is the difference between the radius and cosine, and discovered various trigonometrical identities. For instance, where the Greeks had adopted 60 relative units for the radius and 360 for circumference, the Indians chose 3,438 units and x for the circumference, thereby calculating the ratio of circumference to diameter of about 3.1414. The Surya Siddhanta was one of the two books in Sanskrit that were translated into Arabic in the later half of the 8th century during the reign of Abbasid Caliph al-Mansur. In the next phase, we'll be immersing ourselves in the realm of importance in history of science and exploring its real-world applications. Planet Surya Siddhanta Ptolemy 20th Mangala Mars 686 days, 23 hours 56 mins, 23.5 secs 686 days, 23 hours 31 mins, 56.1 secs 686 days, 23 hours 30 mins, 41.4 secs per Mercury 87 days, 23 hours 16 mins, 22.3 secs 87 days, 23 hours 16 mins, 42.9 secs 87 days, 23 hours 15 mins, 43.9 secs Paspiti Jupiter 4,332 days, 7 hours, 41 mins, 44.4 secs 4,332 days, 18 hours, 9 mins, 10.5 secs 4,332 days, 14 hours, 2 mins, 8.6 secs Shukra Venus 224 days, 16 hours, 45 mins, 56.2 secs 224 days, 16 hours, 51 mins, 56.8 secs 224 days, 16 hours, 49 mins, 8 secs Shani Saturn 10,765 days, 18 hours, 33 mins, 13.6 secs 10,758 days, 17 hours, 48 mins, 14.9 secs 10,759 days, 5 hours, 16 mins, 32.2 secs. Astronomical calculations, estimated time per sidereal revolution. The tradition of Hellenistic astronomy ended in the West after late antiquity. According to Cromer, the Surya Siddhanta and other Indian texts reflect the primitive state of Greek science, nevertheless played an important part in the history of science, through its translation in Arabic and stimulating the Arabic sciences. According to a study by Dennis Duke that compares Greek models with Indian models based on the oldest Indian manuscripts such as the Surya Siddhanta with fully described models, the Greek influence on Indian astronomy is strongly likely to be pre-Ptolemaic. The Surya Siddhanta was one of the two books in Sanskrit translated into Arabic in the later half of the 8th century during the reign of Abbasid Caliph al-Mansur. According to Muzaffar Iqbal, this translation and that of Aryabhatta was of considerable influence on geographic, astronomy and related Islamic scholarship. Get ready for a thought-provoking discussion as we delve into contents and its impact on our understanding. The content of the Surya Siddhanta is written in classical Indian poetry tradition, where complex ideas are expressed lyrically with a rhyming meter in the form of a terse shloka. This method of expressing and sharing knowledge made it easier to remember, recall, transmit and preserve knowledge. However, this method also meant secondary rules of interpretation, because numbers don't have rhyming synonyms. The creative approach adopted in the Surya Siddhanta was to use symbolic language with double meanings. For example, instead of one, the text uses a word that means moon because there is one moon. To the skilled reader, the word moon means the number 1. The entire table of trigonometric functions, sine tables, steps to calculate complex orbits, predict eclipses and keep time are thus provided by the text in a poetic form. This cryptic approach offers greater flexibility for poetic construction. The Surya Siddhanta thus consists of cryptic rules in Sanskrit verse. It is a compendium of astronomy that is easier to remember, transmit and use as reference or aid for the experienced, but does not aim to offer commentary, explanation or proof. The text has 14 chapters and 500 shlokas. It's one of the 18 astronomical Siddhanta treatises, but 13 of the 18 are believed to be lost to history. The Surya Siddhanta text has survived since the ancient times, has been the best known and the most referred astronomical text in the Indian tradition. The 14 chapters of the Surya Siddhanta are as follows, per the much-cited Burgess translation. 1. Of the mean motions of the planets. 2. On the true places of the planets. 3. Of direction, place and time. 4. Of eclipses, and especially of lunar eclipses. 5. Of parallax in a solar eclipse. 6. The projection of eclipses. 7. Of planetary conjunctions. 8. Of the asterisms. 9. Of heliacal sun risings and settings. 10. The moon's risings and settings, her cusps. 11. On certain malignant aspects of the sun and moon. 12. Cosmogony, geography, and dimensions of the creation. 13. Of the armillary sphere and other instruments. 14. Of the different modes of reckoning time. The methods for computing time using the shadow cast by Agniman are discussed in both chapters 3 and 13. As we enter this new chapter, let's navigate the complexities of description of time and unravel its multifaceted nature. The author of Surya Siddhanta defines time as of two types. The first, which is continuous and endless, destroys all animate and inanimate objects, and second is time which can be known. This latter type is further defined as having two types. The first is merta measurable and amerta immeasurable because it is too small or too big. The time amerta is a time that begins with an infinitesimal portion of time truti, and merta is a time that begins with 4-second time pulses called prana as described in the table below. The further description of amerta time is found in Puranas, where Surya Siddhanta sticks with measurable time. Typed Surya Siddhanta units description value in modern units of time amerta truti seconds 29.6296 microseconds merta prana. 4 seconds merta pola 6 pranas 24 seconds merta gatika 60 palas 24 minutes merta nakshatra hotra 60 gatikas 1 sidereal day. Time described in Surya Siddhanta. The text measures a Sovana day from sunrise to sunrise. 30 of these Sovana days make a Sovana month. A solar Sora month starts with the entrance of the sun into a zodiac sign, thus 12 months make a year. The text further states there are 9 modes of measuring time. Of 4 modes, namely solar, lunar, sidereal, and civil time, practical use is made among men. By that of Jupiter is to be determined the year of the cycle of 60 years. Of the rest, no use is ever made. Get ready for an enlightening exploration as we dig into North Pole Star and South Pole Star and understand its role in the broader context. Surya Siddhanta asserts that there are 2 pole stars, one each at north and south celestial pole. Surya Siddhanta chapter 12 verse 43 description is as following. This translates as on both sides of the Meru, i.e. the north and south poles of the earth, the 2 polar stars are situated in the heaven at their zenith. These 2 stars are in the horizon of the cities situated on the equinoctial regions. In this part of the video, we'll be diving deep into the sign table and unraveling its profound impact. The Surya Siddhanta provides methods of calculating the sign values in Chapter 2. It divides the quadrant of a circle with radius 3,438 into 24 equal segments or signs as described in the table. In modern-day terms, each of these 24 segments has angle of no. Sign first-order differences, second-order differences, no. Sign first-order differences, second-order differences, 0, 0. 13, 25, 85, 154, 10, 1, 225, 225, 1, 14, 27, 28, 143, 11, 2, 449, 224, 215, 28, 59, 131, 12, 3, 671, 222, 3, 16, 29, 78, 119, 12, 4, 890, 219, 417, 3084, 106, 13, 5, 1105, 215, 518, 3000, 177, 93, 13, 6, 13, 15, 210, 5, 19, 3000, 256, 79, 14, 7, 15, 20, 205, 6, 23,000, 321, 65, 14, 8, 17, 19, 199, 8, 21, 3,000, 372, 51, 14, 9, 19, 10, 191, 8, 22, 3,000. 409, 37, 14, 10, 20, 93, 183, 9, 23, 3,000, 431, 22, 15, 11, 22, 67, 174, 10, 24, 3,000, 438, 7, 15, 12, 24, 31, 164, 10. Table of signs. The first order difference is the value by which each successive sign increases from the previous, and similarly the second order difference is the increment in the first order difference values. Burgess says, "It is remarkable to see that the second order differences increase as the signs, and each, in fact, is about Earth part of the corresponding sign." Brace yourself for a captivating discussion on calculation of tilt of Earth's axis obliquity as we explore its nuances and implications. Calculation of tilt of Earth's axis obliquity. The tilt of the ecliptic varies between to and is currently. Following the sign tables and methods of calculating the signs, Surya Siddhanta also attempts to calculate the Earth's tilt of contemporary times as described in Chapter 2 and verse 28, the obliquity of the Earth's axis. The verse says the sign of greatest declination is 1397. By this multiply any sign, and divide by radius. The arc corresponding to the result is said to be the declination. The greatest declination is the inclination of the plane of the ecliptic, with radius of 3,438 and sine of 1397. The corresponding angle is or 5830.65, which is approximated to be. As we enter this new phase, let's uncover the impact of planets and their characteristics on our broader topic. The text treats Earth as a stationary globe around which Sun, Moon and 5 planets orbit. It makes no mention of Uranus, Neptune and Pluto. It presents mathematical formulae to calculate the orbits, diameters, predict their future locations, and cautions that the minor corrections are necessary over time to the formulae for the various astronomical bodies. The text describes some of its formulae with the use of very large numbers for Divya Yuga, stating that at the end of this Yuga, Earth and all astronomical bodies return to the same starting point and the cycle of existence repeats again. These very large numbers based on Divya Yuga, when divided and converted into decimal numbers for each planet, give reasonably accurate sidereal periods when compared to modern-era Western calculations. Surya Siddhanta modern values: Moon 27.322 days, 27.3216 days, Mercury 87.97 days, 87.969 days, Mars 687 days, 686.98 days, Venus 224.7 days, 224.701 days, Jupiter 4,332.3 days, 4,332.587 days, Saturn 10,765.77 days, 10,759.202 days. Sidereal periods. Now it's time to shift gears and explore calendar. The solar part of the lunisolar Hindu calendar is based on the Surya Siddhanta. The various old and new versions of Surya Siddhanta manuscripts yield the same solar calendar. According to J. Gordon Melton, both the Hindu and Buddhist calendars that are in use in South and Southeast Asia are rooted in this text, but the regional calendars adapted and modified them over time. The Surya Siddhanta calculates the solar year to be 365 days, 6 hours, 12 minutes and 36.56 seconds. On average, according to the text, the lunar month equals 27 days, 7 hours, 39 minutes, 12.63 seconds. It states that the lunar month varies over time, and this needs to be factored in for accurate timekeeping. According to Whitney, the Surya Siddhanta calculations were tolerably accurate and achieved predicted usefulness. In Chapter 1 of Surya Siddhanta, the Hindu year is too long by nearly 3 minutes and a half, but the moon's revolution is right within a second, those of Mercury, Venus and Mars within a few minutes, that of Jupiter within 6 or 7 hours, that of Saturn within 6 days and a half. The Surya Siddhanta was one of the 2 books in Sanskrit translated into Arabic during the reign of Abbasid Caliph al-Mansur. According to Muzaffar Iqbal, this translation and that of Aryabhatta was of considerable influence on geographic, astronomy and related Islamic scholarship. Prepare yourself for an in-depth analysis of editions in this section. The Surya Siddhanta, an ancient system of Hindu astronomy edition Fitz Edward Hall and Lāṭadeva Astron 1859. Translation of the Surya Siddhanta, a textbook of Hindu astronomy, with notes and an appendix by Ebenezer Burgess, originally published, Journal of the American Oriental Society 6, 1860. Commentary by Burgess is much larger than his translation. Surya Siddhanta, a textbook of Hindu astronomy translated by Ebenezer Burgess, edition Fanindralal Ganguly with a 45-page commentary by P. Celsius. Sengupta 1935. Translation of the Surya Siddhanta by Lāṭadeva Sastri 1861. Only a few notes. Translation of Surya Siddhanta occupies first 100 pages, rest is a translation of the Siddhanta ceremony by Lancelot Wilkinson. Now, it's time to shift gears and explore commentaries. The historical popularity of Surya Siddhanta is attested by the existence of at least 26 commentaries, plus another 8 anonymous commentaries. Some of the Sanskrit language commentaries include the following. Nearly all the commentators have rearranged and modified the text Surya Siddhanta Tika 1178 by Mallikarjuna Suri, Surya Siddhanta Bhashya 1185 by Chanishvara, Amathila Brahmana Vesananavasi by Maharajadraja Madnapola of Taka family, Surya Siddhanta Vivrana 1432 by Parameshvara of Kerala, Kalpavali 1472 by Yolaya of Andhra Pradesh, Subodhini 1472 by Ramakrishna Aragya, Surya Siddhanta Vivrana 1572 by Madhara of Kampalia, Kamododri 1599 by Tamayojan of Paradapuri, Gohatha Prakashika 1603 by Ranganatha of Kashi, Sura Bhashya 1611 by Nsimha of Kashi, Gahanafa Prakasha IAST, Girtha Prakaka 1628 by Vishwantha of Kashi, Sura Vasana after 1658 by Kamalakara of Kashi, Karanavali 1719 by Dedabay, Chipavana Brahmana Surya Siddhanta Tika date unknown by Tomabat of southern India, Ganatopakarini date unknown by Cholabhakashit of southern India, Garugateksha date unknown by Bhuti Vishnu of southern India. Mallikarjuna Suri had written a Telugu language commentary on the text before composing the Sanskrit language Surya Siddhanta Tika in 1178. Kalpakirti Alanoriya Suri wrote another Telugu language commentary on the text, known from a manuscript copied in 1869. I love interacting with my viewers, so leave me a comment and I'll do my best to respond.